Hi everyone, this is K. Karthik from Institute of Aeronautical Engineering, Electrical and Electronics Engineering from Section A, 2395180206. Now I am going to discuss about guide for selecting, charging, testing and evaluating lead-acid batteries used in stand-alone photovoltaic PV systems. Guide for selecting, charging, testing and evaluating lead-acid batteries used in stand-alone photovoltaic PV systems. Lead-acid batteries are common energy storage solution for stand-alone photovoltaic PV systems, providing reliable backup power when the sun is not shining. This section provides an overview of the key considerations in selecting, charging, testing and evaluating lead-acid batteries for off-grid solar applications. Battery selection criteria. Battery type. Choose between flooded lead-acid sealed AGM, absorbed glass mat, or gel-based batteries based on their unique characteristics such as maintenance requirements, cycle life, and tolerance to overcharging. Battery capacity. Determine the required battery capacity by considering the energy needs of your PV system, load profile, and desired run time during periods of low solar insolation. Depth of discharge. Selecting batteries that can handle the desired depth of discharge DOD without significantly reducing their lifespan. Higher DOD provides more usable energy but can shorten the battery's overall life. Environmental factors. Consider the operating temperature, range, humidity and ventilation requirements of the battery location to ensure optimal performance and safety. Battery sizing consideration. Power requirements. Determine the total power needed to run your stand-alone PV system, including peak and average daily energy consumption. Battery capacity. Calculate the required battery capacity based on your power needs, anticipated usage patterns, and desired backup duration. Depth of discharge. Consider the maximum depth of the discharge to ensure the battery longevity and prevent premature failure. Ambient condition. Account for environmental factors like temperature, which can impact battery performance and lifespan. Battery charging techniques. Constant voltage charging. This technique applies a steady voltage to the battery, allowing it to charge at the gradually decreasing current until it reaches full capacity. A constant voltage charger is basically a DC power supply, which in its simplest form may consist of step-down transformer from the mains with the rectifiers to provide the DC voltage to charge the battery. Such simple designs are often found in cheap car battery chargers. The lead-acid cells used for cars and backup power systems typically use constant voltage chargers. In addition, lithium-ion cells often use constant voltage systems, although these usually are more complex with added circuitry to protect both the batteries and the user safety. Constant current charging. A fixed current is supplied to the battery, which is then switched to a lower float voltage once it's fully charged. Constant current chargers vary the voltage they apply to the battery to maintain a constant current flow. Switching off the voltage reaches to a level of full charge. This design is usually used in nickel cadmium and nickel metal hydride cells or batteries. Multi-charging. Combine constant current and constant voltage phases to optimize charging, ensure full capacity, and prevent overcharging. Taper current. This is charging from the crude unregulated constant voltage source. It is not controlled charge as in V taper above. The current diminishes as the cell voltage back EMF build up. There is a serious danger of damaging the cells through overcharging. To avoid this, the charging rate and duration should be limited. Suitable for SLA batteries only. Pulse charging. Apply short high current pulses to the battery, allowing it to absorb charge and efficiently and reducing gassing. Pulse charger speeds the charge current to the battery in pulses. The charging rate, based on the average current, can be precisely controlled by varying the width of the pulses, typically about 1 second. During the charging process, short rest period of 20 to 30 milliseconds between pulses allow the chemical actions in the battery to stabilize the equalizing the reaction throughout the bulk of the electrode before recommencing the charge. This enables the chemical reaction to keep pace with the rate of inputting and electrical energy. It is also claimed that this method can reduce unwanted chemical reactions at the electrode surface, such as gas formation, crystal growth, and passivation if required. It is also possible to simple the open circuit voltage of the battery during the rest period. Battery charging algorithms. Constant current charges battery at fixed rate current rate. Constant voltage maintains a fixed voltage to avoid overcharging. Multi-stage combines constant current and constant voltage phases. The choice of battery charging algorithms is critical to ensure the battery is charged efficiently and safely. Constant current is simple but can overcharge the battery, while constant voltage protects against overcharging but may take longer. Multi-stage algorithms balance these trade-offs by using both techniques at different stages of state cycling. A charge algorithm defines a series of steps to control the characteristics of electrical power supply, configuring to perform the functions of a battery charge. More specifically, the focus is on the output characteristics of voltage, current, and time. Battery monitoring and testing. Continuous monitoring, periodic testing. Continuous monitoring. Install a battery monitoring system to track a key matrix like voltage, current, temperature, and stage of charge. This provides real-time data to optimize performance and detect issues early. Periodic testing. Conduct a regular battery capacity test to measure the remaining useful life. This involves fully discharging and recharging the battery to assess its ability to hold a charge. The simple battery monitoring is a scalar concept. Scalar monitoring takes a single reading and compares it to a single reference point to generate the estimate of battery capacity. A car battery analyzer is a common example of testing systems which often uses the scalar systems. Battery maintenance and troubleshooting. Regular inspections, battery watering, equalization, charging. Regular inspections. Regularly inspect your lead acid batteries for signs of damage, corrosion, or wear. This helps ensure optimal performance and longevity. Battery watering. Monitor and maintain the proper electrolyte levels in your batteries. Add distilled water and needed to keep the plates submerged. Equalization charging. Perform periodic equalization charging to balance the state of charge across all cells and prevent sulfation buildup. Regular maintenance is vital to keep these batteries clean and working optimally. Inspections every 2 to 4 weeks and maintain properly water levels and clean terminals are crucial for these batteries. Following the manufacturer guidelines for charging lead acid batteries will ensure optimal performance and longevity. Battery replacement and disposal. When to replace batteries, proper disposal, sustainable replacement. When to replace batteries. Replace lead acid batteries when their capacity drops below 80% of the original rating, typically after 5 to 10 years of the use in a stand-alone PV system. Proper disposal. Recycle lead acid batteries through authorized recycling facilities to recover the valuable materials such as lead and sulfuric acid and prevent environmental contamination. Sustainable replacement. Consider upgrading to more efficient and environmentally friendly batteries. Techni- Technologies like lithium ion when replacing lead acid batteries in your stand-alone PV system. Batteries that can still be reused must not be discharged with dead batteries. If still functional, they can be used in other devices or donated to retailers who accept them for further recycling. This helps in reducing and wasting and also extends the life of batteries. Economic and environmental factors. Lead acid batteries used in stand-alone PV systems have significant economic and environmental implications. Their initial cost, maintenance requirements, and disposal considerations must be carefully evaluated to ensure cost effectiveness and sustainability. Battery purchase cost up to $400 to $600. Environment impact is is 0 to $200. Installation is approximately $200 of cost and impact is up to 0 to $200. Maintenance is up to 0 to $200 of cost and 0 to $200 of environment impact. And replacement $200 to $400 of cost and environment impact is 0 to $200. Disposal cost 0 to $200 of and environment impact is 0 to $200. The chart highlights the key economic and environmental factors associated with lead acid batteries in stand-alone PV systems, including the initial purchase, installation, maintenance, replacement, and disposal costs, as well as environment impact of each stage. The economic environment of business is one of the external factors that can influence the strategy and decision making. Economic factors including GDP, exchange rates, taxation, interest rates, fiscal policy, monetary policy, and inflation. This business cycle is an important tool for understanding how economic works. Conclusion and key takeaways. Reliable power storage, sustainability consideration, bright future for PV systems. Reliability power storage. Lead acid batteries play a crucial role in stand-alone PV systems, providing reliable and cost-effective energy storage for renewable energy applications. Sustainability considerations. Proper battery maintenance, recycles, and disposal are essential for minimizing the environmental impact and ensuring a long-term sustainability of lead acid battery usage in PV systems. As renewable bright future for PV systems as renewable energy technologies continue to advance. The importance of effective energy storage solutions like lead-acid batteries will only grow, supporting the widespread adoption of standalone PV systems. The end.